Now we're ready to see Dijkstra's algorithm a little bit more specifically with an example here. We're going to see how this is actually run. So I got an example of a graph here, a weighted graph, and again the goal is going to be to get from A to Z as efficiently as possible, as quickly as possible. So the way Dijkstra's algorithm works, it's simple to write down, but we'll run through a couple examples to get a sense of how this works. So at the beginning of the problem, you first set initial distances. So for each node in the graph, we're going to set an initial distance. And the way we do this is A gets a distance of 0, meaning that's where we're starting. So from the origin, since A is the origin, that gets a distance of 0 from itself. And then everything else, we set the distance to infinity. In other words, as things stand to begin, we just set it as a huge number, and the goal is we're going to cut these distances down by finding shorter paths to each one of them. So we start with a distance of 0 at A, and then everywhere else we mark with infinity, just to begin with. So you'll see as we go through this why we do that, but again, the idea is basically at each stage we're going to look to see if we can find a shorter path to each node, and of course we can find something shorter than infinity to any one of them. So that's how you start it out. And then the process of the algorithm, the part that gives the algorithm the name of an algorithm, the repeated step that you go through, is you pick the node from all those remaining that has the smallest distance currently. So on the first step you would pick A because that has the smallest distance of all of them, the others are infinity. So you pick the one with the smallest distance, and then what you do is you update the distances to all their neighbors, all its neighbors. Meaning you look to see, can I find a shorter path from this point to its neighbor than what it currently has? You'll see that as we go through and practice how this works. And then once you've done that, you check off that node, meaning you've finished with it. You've visited it, you've checked it, you don't need to come back and look at it again. And then you repeat this until all the nodes have been visited. So the idea is we instead of accounting for all possible paths from A to Z, we just have to account for all the nodes in the graph, which is a much smaller number of things to account for. So that's kind of the beauty of this algorithm, that it gives us that shortcut. So let's actually see this in practice, because just seeing the steps written out like this is not nearly as instructive as seeing an example. So we'll take this example, and I've drawn it again for you, with the initial distances set from A to each one of them. So these distances that are listed are the distance from A, the shortest distance you've found so far. So what I'm going to do here is list out the nodes. So we have A, B, C, D, E, and Z. And then the current distance of each of them, they're starting out at infinity, everything other than A. All right, so the algorithm says pick the node with the smallest distance, so that would be A currently, update the distance to all its neighbors, and then check it off. So what we're going to do is we're going to say the neighbors of A are B, C, and D, right? These are the ones that border A, that are connected directly to it. So we're going to update the shortest distance we can find from A to each of those points, which would be the direct path to each one. So B, we can get there from A with a distance of 14. So we'll cross this off and say we have 14 by going A to B. Then, I guess I'll do it this way. Then C gets the same treatment. So rather than infinity, we can find a shorter path, which will get us there in 9. And then D has a distance of 7. Sorry, this should be AC. All right, so we can get directly to each one of them. So I'm going to erase these current weights, or current distances, and replace them with 14, 9, and 7. So now we can check off A as being done, and now we're going to select of all the nodes left that we haven't visited yet, which one has the smallest distance. That would be D. And so we're going to repeat the process. Now from D, we're not going to visit A again because we're done with that one. So we're just going to look at updating C and updating E and see if we can find a shorter distance from A. So the idea here is we're going to say from D, if I go up to C, what I'm doing is starting at A, going to D, and then going to C. So I would take the distance that's currently at D and add this cost of traveling to C, and if that were shorter than going directly there, I would update it. So in other words, if I got here with 7, and then say this only cost me 1, then I would say, look, I can get to C faster if I do this than if I go directly there from A. And so I would update the distance at C and say I can get there faster from passing through D. Now that's not the case currently, because if I add the current D distance plus the additional 10, I get 17, which is not less than this, so I don't update that. So that second step where we say we update the distances, what we're looking for is to see if we can see if the distance through the node we're interested in right now is shorter than the current distance to its neighbor. So that didn't make sense. We'll go through more steps and you'll see it again. So C we don't do anything with, we leave it alone. But E, we notice that from D we have a distance of 7 so far, and then an additional distance of 15 for a total of 22, which is definitely less than infinity. And again, this is why we set the initial distances to infinity, so that they'll get initialized the first time they get checked. So E, we can get there in 22 by going A to D to E. So having checked all the neighbors of D, we check it off, and we replace the distance at E with 22. All right, so now we look through our list again and see which ones of the unvisited ones has the lowest current distance, and that would be 9 with C, not with 9. So we're going to go to C, and we're going to check its neighbors. Now we've already checked off A and D, so we're going to leave those alone, but we'll check B and E, and we'll see if we can get there to either one of those shorter than what the current best path to those is. So from C, if we go up to B, notice that we have 9 to get to C, an additional 2 costs us 11, which is better than the current 14 at B. So we're going to cross out the current B, and we have a total of 11 by going A to C to B. So it's faster to get to B by going through C than it is to get there directly. So going there directly costs 14, taking this side route costs 11. So we can update the distance there and say that's just going to be 11. We can do the same thing to go to E. We've got 9 so far. If we add 11, we'll get 20, which is better than the current 22. So again, we're going to cross out the 22 and replace it with 20. And that does the same thing here. So E, we can do better than 22. We can do 20 if we go A to C to E. Having done that, we've checked all of C's neighbors, and so we can mark off C. And now again, we look through and say which of these unvisited ones has the lowest distance. There's only 3 left, and the lowest one we find is B. And so we go to B and check its neighbors. So the only neighbor of B that we haven't checked yet is Z. So we'll check that one. Since Z hasn't been visited yet, we'll certainly update that distance. The current cost of going to B is 11, and if we add 9, we get a total of 20. So we can get to Z with 20. So we can check off B, and we'll update the cost of going to Z with 20 by going, now notice the shortest distance to get to B is going through C. So if we go A to C to B to Z, that's currently the shortest route to Z. And then one last step, we'll check going through E. Now, if you notice, so that's our next lowest one that we haven't checked off yet. If you notice, the distance to E is already 20, so going up to Z would add 6 to that, which is not better than the current optimal route. So the final answer is that our optimal route, the best path, would be to go A to C to B to Z, and the cost is 20. So that's really how Dijkstra's algorithm works in short. And again, it takes us longer to do it than it takes a computer to do it if you program it to do this. It's very efficient because we only had to really check a handful of nodes rather than accounting for all possible paths, which just very quickly gets out of hand. So there's our first example of seeing Dijkstra's algorithm at work. Here's the description of it. You start with the initial distances, and then at each step you pick the smallest distance remaining and update the distance to all the neighbors before checking it off. So I want to do one more example just to kind of drive this home again. This one looks much more complicated, and this, if you notice, there are lots of paths that would be possible through this graph because it's so connected. There's so many connections going on here. But with this algorithm, we can do it pretty quickly, about as quickly as we did the last one. So I'm going to do something similar here, where I'm going to list out all of the nodes, and we'll keep track of their current distance at each stage of the process. All right, so at the beginning, we start out with 0 and infinity for all the others. So again, we're starting at A and trying to get to Z. So all of these start out with infinity, just as the initial value, and then we'll update as we go. So we start with A, the shortest current distance, and update its neighbors. So the neighbors of A are C, D, and B. And so we can update B, for instance, has a distance of 5 if you go directly from A to B. C has a distance of 3 if you go directly from A to C. And D has a distance of 7 if you go directly from A to D. So then we check off A, and of the smallest ones remaining, we notice C is the smallest one. So looking at C, what is it connected to? It's connected to A, which we've already checked, and then D and F. So if we went from C, from the current cost it has, to D, that would add 1, which gives us a total of 4, which is better than the current cost that D has associated with it. So if we go from A to C to D, we're better off than going straight from A to D. And then from A to C to F would be a total of the 3 that C currently costs, plus 7 to go from C to F, for a total of 10, which is better than infinity. And then we can check off C as being done. Then again, of those remaining, D is the smallest. So we can look into the neighbors of D. D, we've already checked off A and C, so we're not going to go back there. But we can go to B, F, G, or E. So again, I don't want to spend a lot of time going through the details here. If you go from D to B, that adds a total of 3, which gives you 7 total, which is not better than the current distance to B, so we'll leave that alone. From D to F would give you a total of 6, which is better. So if we went from A to C to D to F, so we're taking this current path to D and then just tagging on the distance to F. And then to E would be a total of 7, because we're adding 3 to get there. So that would be, if we went from A to C to D to E, that would be a total of 7. And then lastly to G would be a total of 5. So we've done all of the neighbors of D, so we can check that off as well. And then just a couple more steps. Won't take too much longer. The shortest one that remains of the ones we haven't checked off yet is B. From B, the only neighbor we haven't checked off yet is E. That would be a total of 7, because we have the 5 currently to B and 2 more to get to E. That matches what we have currently, so we won't bother updating it. There's no benefit to updating it, even if it keeps the same distance. So we'll leave that alone, check off B, and we're done. The remaining smallest is G, so we'll check the neighbors of G. Notice that from G you can get to Z with 2, you can get to E with 3, you can get to F with 2, and H with 3. So that would, to go from G, which currently has 5, up to F would give us 7, which is not better than what we have currently. To go to E would give us 8, which is also not better than we have currently. To go to H would give us 8 also, which is better than we have right now. And then to go to Z would add 2, so that would give us a total of 7. All right, so we've checked off G now. Now we can keep trying this, but you're going to notice that any of the current remaining ones, the shortest distance to any of the other ones, at best, the shortest distance is 6. So if F takes any more than 1 step to get to Z, which it definitely does, then you're not going to beat the current best distance. So we can stop here, and the best path we're going to find is to go from A to C to D to G to Z, and that's the optimal route. So the optimal route looks like this, where we go from A to C and then down to D, and then to G, and down to Z. So there's your optimal route. So again, we're doing it by hand here. More reasonably, you would write a program to do this for you more efficiently. But it gives us the sense of how Dijkstra's algorithm works. And again, any mapping software you use that finds a route from A to Z is using some sort of variation on this, or an algorithm that adds some extra pieces to this. But this is the foundational piece that really governs navigation like this.